break, I left you kind of with a cliffhanger, and I'm sure you spent all spring break waiting anxiously. Probably not, but so actually, before we get to that, kind of as a way to get back into it and just remind ourselves what we're talking about, and to motivate the next thing we're going to talk about once we finish, I have a scenario for you. So imagine that I have, I can't draw, so I'm going to put, it's a frog, but I'm just going to put an F. Okay. Just imagine that's a frog. And the frog is sitting on the number line. Okay, so it starts at 0, and the frog can make certain jumps, left or right. So let's say this frog, it can jump 30 units in either direction. So it can make like big jumps and small jumps, or maybe we'll call them jumps and hops. Okay, so it can jump 30 units in either direction, and it can hop 18 units in either direction. It's very specific. So I don't know, maybe like I don't know why it can't jump other distances, but it can. So the question is, which places on the number line is it able to reach? Okay. So obviously it can reach 30, or it can reach -30. It can reach 18, -18. But for example, it could also reach 60, because it could jump 30 and then it could jump 30 again. It could also reach like 12, because it could jump 30 to the right and then it could jump 18 to the left. Right, so it could go, if it went back 18 this way, it would end up here at 12. Right? So, so it can reach 30, it could reach 60, it could reach 12, it could reach, 48, and obviously all the negatives of those. So where else can it, it can reach 18, of course. Where else can it reach? Garrett?
It could reach 6 because
Can it reach 6?
12, jump back 18 to -6, and then jump forward 12 again to get to 6.
It can't jump 12.
Oh, right.
Can it? So can it reach 6? So that doesn't prove that it can't reach 6, but it can get to -6. Okay, how could it get to -6? Oh, you mean go here to 12 and then just jump 18 again? Okay. Yeah, good. I agree. So let's do another 18 here. That is -6. So can it reach +6? Yeah, I mean, since any of the jumps and hops it can do in either direction, if it just does the same thing, like whatever it just did to get to -6, if it just does the same thing but all in the opposite direction, like, so I guess it would start going 30 this way, and then 18, and we get to +6. Can it get to, so it can get to 6, 12, 18, could it get to 24? That would be like, in between 18 and 30, right? Could it get to 24?
Yes.
Yeah.
Yes, why?
So if you do the thing to get to 6,
Uh-huh.
I forgot to make that.
Yeah, whatever. We know we can get to 6.
The 30
yeah.
back and then
Yeah.
up for 18 twice, and then we can up for 18 again. So it's 24.
Okay, all right, yes, you can go from 18 to get from 6 to 24. Okay, cool. How about, how about like 612? Do you think it can get to 612? So I'm not looking anymore for like, you don't have to tell me a specific sequence of jumps and hops because that would be tedious. But like, can you give an argument why it can or can't get there? And basically, you were nodding that.
You can get to 600 just because 600 is a multiple of 30,
Uh-huh.
and then you can get to 12 just by 30 minus
say like, whatever sequences of jumps and hops we did to get to 6, we could call that something new. We could call that a skip or something. And you could just say, just keep doing skips. And like each skip, it would, do some things, but it would get 6 further down the line, and it would get any multiple of 6. Okay, cool. How about 3? Can we do 3? Can I get to 3? So any multiple of 6. Sure. See some people shaking their head. People thinking hard. Anyone have an argument why we can't reach 3, other than I tried some things and it didn't work? Max?
Can't get to any negative number because it only moves in positive numbers. There's no way for it to.
No, it can jump backwards. It can jump either direction.
Not negative, but like odd.
Oh, it can't get to odd numbers. Oh, why is that? I agree.
It only jumps at even.
Okay, yeah. It only jumps in 30 and 18 are both even. And if you're just always doing even things, you'll only get to even numbers. Cool. I agree. So no, we can't get to 3. How about 4 then? 4 is even. Sorry?
I don't think so. And is it because it's like, to go with like the multiples, it's like 30
You are very much on the right track. So, so the thing you just said doesn't quite work, because like, for example, we can get to 12. 30 and 18 are not multiples of 12, but we can still get to 12 anyway, even though they're not multiples of it, right? But you're right that we can't get to 4. It has something to do with multiples. So, Dale?
So from negative 30, if it jumps forward 18, that's 12.
Negative 12, yeah.
Never mind.
Yeah, okay. And if you jump forward again from there, you would get to 6. Did you ever hand up, Matthew?
I did. I was going to say, it could only get to multiples of the LCM.
Okay, so the least common factor, or the greatest common divisor. The least common multiple of those things would be like some big number.
Yeah. Like in this case, it would be 6. Like
Right. Okay. So we can say they're both 30 and 18 are both multiples of 6. And so by a very similar argument to what Max was saying about that they're both even, since they're both even, we can only get to even numbers. But more than that, since they're both multiples of 6, we can only get to multiples of 6. Right? Because anytime you add or subtract a multiple of 6, or a multiple of 6, you'll get a multiple of 6. So yeah, it's not possible to get 4. So in this case, right, we saw that 30 and 18 are both multiples of 6, so we can definitely only get multiples of 6. We also already argued that we can get any multiple of 6, right, because we saw we can get 6, and so from there we can just do that any number of times and get any multiple. So in this example, it looks like, well, then we are in 30 and 18, we already know that 6 is in fact the, it's not only a common divisor, it's the greatest common divisor. And so in this case, we can get to any multiple of their greatest common divisor. Now, the question is, is that always, if I pick two other numbers? So certainly, we can only get to things, let's see, how do I say this? There's one direction that's easier and there's one direction that's not as obvious. Okay, let's say I have two numbers. So, in general, right, if I have, here's my frog, it can do like, some jumps of length A and some jumps of length B in either direction, right? And let's say that G is the greatest common divisor of A and B. Question is, can we always get to all multiples of that? So, I'll just leave it at that for now. We're going to come back to this. The answer, it turns out, is yes. But it's not necessarily obvious that we can always do that, right? Because what we're saying is there always some combination of A's and B's that I can do a bunch of A's and maybe subtract some B's and get to their greatest common divisor. It's not obvious that would be the case, right? Because in this case, right, I had to do subtract 30 and then add 18 twice, and I got to 6. But maybe there's no way in general to do that. But it turns out it's always possible, and that fact is an important fact about how the GCP works. All right, so that was just kind of to whet your appetite, get us back into it, and to remind ourselves that we're talking about the greatest common divisor, right? And last time we talked about one way to compute the greatest common divisor, which is if you factor both numbers, right, then you can just look and see what prime factors they have shared between them, and that would give you their greatest common divisor. But I claim that's not an especially efficient way to do it, especially if A and B are large, because factoring numbers is difficult to do. Like, no one knows a fast way to do it, basically. You kind of just have to try everything. Like, no one really knows a better way to do it fundamentally. Well, not entirely true, but no one knows like a really much better way to do it than kind of just trying all the possible divisors and see. So it turns out there is a better way to compute the GCD, and it's called the Euclidean Algorithm. It's named after Euclid, who's an ancient Greek mathematician. He's famous for writing this this big work that kind of, it's unclear exactly how much stuff was stuff that he came up with and how much was stuff that other people had done, and he kind of compiled it all. But in any case, he kind of compiled all this stuff into a very coherent framework, and really it was the basis of kind of a lot of the way that we think about proofs ever since. In terms of, he started from some axioms and he kind of logically derived each thing from previous things. Anyway, and so in that giant work called Euclid's Elements, one of the things in there talks about this algorithm. Now, he certainly didn't come up with it himself. I'm sure people knew about it before that, but it has his name because that's kind of the most famous place that it's described. In a sense, you could think of this as one of the oldest computer programs that was ever written down. Not in the sense that, of course, they didn't have computers, not the way we think of computers, but it was definitely an algorithm in the sense of a step-by-step method for computing something. And it's one of the oldest examples we have of such a step-by-step algorithm being written down. So, how does it work? Well, there's a couple facts about GCD that I'm going to tell you, and then from that we'll be able to figure out how the algorithm works. So, here's a lemma. And a lemma is just like a baby theorem that you don't really care about. You just care about it in order to prove something else. But it's really the same thing. This just says the GCD of AB is equal to the GCD of BA. I'm not even going to bother proving this because if the greatest common divisor of A and B is something, it really doesn't matter what order I say them in, right? They have the same common divisors either way. And if you want to do a formal proof, you basically look at the definition of GCD and you say, look, the definition doesn't make any distinction between A and B. It's completely symmetric. So if I switch them, like, the definition is the same. I guess formally it would come down to the fact that and is also symmetric or something. But so theorem. So, and I'm not gonna prove this one to you formally, but I'll draw a little picture and hopefully convince you. So if I have some natural numbers A and B, then for all integers k, the GCD of A and B is equal to the GCD of A plus k times B. So in English, this is saying if you're looking at the greatest common divisor of two numbers A and B, you can add any number of copies of one to the other, and that doesn't change their GCD. Right? So in this case, I'm saying, look, I can take B and add it to A as many times as I want, or subtract it. K could be an integer. Add or subtract as many times as I want, and it won't change the GCD at all. And it doesn't, right, and because of this, the order of A and B doesn't matter, so it doesn't really matter whether we add the second one to the first one, or add the first one to the second one, because we could just switch them, it doesn't matter. I'm not going to prove this to you, but it's in the lecture notes PDF if you wish to look at it. It's not necessarily a hard proof. You can just apply the definition of GCD, and you have to prove that, something divides something else, and you prove that some things divide each other, which you do by saying, well, we can find out what K is supposed to be. You can kind of follow through the definitions. But I'm not going to do a formal proof, but I'll draw a little picture and hopefully convince you why this is true. So if I have, here's A, and here's A, and here's B. And maybe, right, their greatest common divisor is, maybe it's like, maybe something like this, right? So maybe this is, I'll call this G. So G, right, it's the biggest, in terms of this picture, it's like the longest line segment I can make that will, exactly fills up, some number of copies in A, and also exactly fills up B with some number of copies. If I make G any bigger, then I won't be able to exactly fit it into one or the other. And so what would happen if I add them? So like here's A plus B. Maybe like here's A plus 2B. And here's B again. I'm running out of space, but this is A plus 2B. And this is B. Right? Well, look, G fit exactly into A, and it also fit exactly into B. So it's going to fit exactly into A plus 2B, right? Well, there'll be 3 copies in here. And, 5 copies in here, 5 copies in here, and 5 copies in here. So, it's not too hard to see that if G was a common divisor of A and B, then it's also going to be a common divisor of, when I add some number of B's to A, it's still going to be a divisor of that. And the other question is, why is it still the greatest common divisor? Like, why can't I now fit something bigger in there? Well, maybe that's not as obvious from the picture, but that's true. That's true also. That's where you would really need the proof to see that for sure. But. Okay. Cool. And then here's one more theorem. And then we're just going to be able to put these 3 theorems together to directly write down what the Euclidean algorithm is. Okay. So this theorem says let A and B be natural numbers. Then GCD of A and B equals GCD of B, comma, A mod B. What is A mod B? Remember, that just means the remainder if we divide A by B. Why is this true? Well, really, I'll write down a proof in a second, but just think about it for a second. It's true because of this theorem. So what is A mod B? A mod B says if you divide A by B and what's left over. You could also think of that as like subtract copies of B from A until you can't anymore and see what's left, right? Well, this theorem already says, look, you can subtract copies of B as much as you want from A and it won't change the GCD. So this is just saying, yeah, keep B the same and then just subtract as many copies of B as you can from A. And then that theorem tells us it'll be the same. Right, so formally I could say, proof by the division algorithm we could say that A equals BQ plus R. Right, the division algorithm says you can always say that A equals some number of copies of B plus a remainder. And those are unique, right? And then say that GCD of AB equals GCD of BQ plus R, which is equal to, this is by the above theorem, GCD of, well, I'm going to say BQ plus R, and then I'm going to subtract some number of copies of B from this. How many copies do I want to subtract? How about Q? That sounds nice. Right, and that theorem that we proved above, well, we didn't prove it. The theorem that I stated above says we can subtract as many copies of this B as we want from this side, and that doesn't change the GC. The BQ's cancel. Right, this just says GCD of RB. And, well, I can switch these around, B comma R. Right, because GCD is commutative. Well, R, what is R? R is just the remainder when we divide A by B. Right. Another way to write that is A mod B. That's what the R represents. Okay. Any questions? Makes sense? Okay, here's the interesting thing. Here's how we're going to turn this into an algorithm. notice, so here I started out with GCD of A and B, and here I have the GCD of B and A mod B, which was the R from the division algorithm. What does the division algorithm tell us about R? Right, the division algorithm says something about like, oh, there's an R that is within a certain range. Does anyone remember what that is? When we divide A by B, we get some quotient Q and a remainder R, and what range does the R have to be in? Kathy?
0 and B.
Between 0 and B? Can you be slightly more specific?
R is,
Like, can it actually be equal to 0 or B?
can be 0 and
Yeah, that's right. Right. In particular, when we're dividing by B, the remainder is going to be less than B, right? Because if it was B, then we didn't divide enough times. Like, we could have fit one more B in. So the remainder always going to be less than B. Okay, that's the important point. So we started here with GCD of A and B, and here we have A mod B. That's the remainder when we divide it by B. That's less than B. So that means if we do this, we end up with this second thing is smaller now. Okay, so if we do this again, the second thing will get smaller still. It'll keep getting smaller, which means it can't keep getting smaller forever. Okay, and that means this is actually a viable, like repeating this is actually a viable algorithm. It won't just like keep repeating forever. It'll actually stop after some number of steps. Okay, so that's what we're going to do. Now, we need to say what happens when we get to 0. Well, what's the greatest common divisor of A and 0? It's A. Right, exactly. So that's easy. That's our base case. So let's open the page. So, or I'll say definitions. The Euclidean algorithm. So let A and B be natural numbers to find GCD of A and B. Repeatedly apply these rules. So first of all, GCD of A and 0, anything divides 0, and A divides itself, so that's always A. Right? And GCD of A B is GCD of B A mod B. That's it. That's the algorithm. And right, again, the reason that this is a valid definition is that A mod B we know is always smaller than B. And so we don't know what will happen to this first thing, but the second thing is going to get smaller every time. So if we keep doing this repeatedly, the second thing will get smaller and smaller. Since these are natural numbers, they can't keep getting smaller forever, right? Eventually, it'll have to get to 0, and then it'll stop. Right, and it's important that they're natural numbers. So first of all, if they were integers, an integer getting smaller could keep getting smaller forever because it could be negative. And if it's like a rational number, for example, rational numbers can keep getting smaller forever because you could say like a half, a quarter, an eighth, a 16th, right? You could always get closer and closer to 0 to never get there. But for natural numbers, you can't do that. So, just say notice notice, this actually looks a lot like the way you might define a function in Disco. And indeed, this literally would be a valid Disco definition of GCD. And I'll probably have you do that on the next module. You have to give it a type and stuff like that, but and notice I don't think we've done this before. I don't think we've written Disco functions that call themselves, right? So notice that GCD here is defined in terms of itself, but that's perfectly okay. Again, as long as something is getting smaller all the time, it won't keep going forever. This is fine. Disco will very happily run a recursive function that is defined in terms of itself, because that's something we do often in math. So let's do some examples. Well, let's start with our good old standby of 60 and 18, which we already know should be, or maybe I was doing 30 and 18 before. Well, we'll do 60, whatever. We know this should be 6, but let's just see how it works. Well, 18 is not 0. I hope you agree. So we can't use that first rule, so we can use the second rule. Okay, so by the second rule, this should be equal to GCD of B, which in this case is 18. And what's 60 mod 18? Well, we could use a calculator, or we can think hard. I mean, if we...
60 minus 54, so 6.
So 6, okay. So right, so 54 is a multiple of 18. I guess, yeah, that's 18 times 3. So the remainder would be 6. Okay. But I'll write it out just so if you're looking at the notes later, you'll be like, how did we get 6? This is 60 mod 18, right, which is GCD of 18, 6, okay? 6 is still not 0, so use the second rule again. So this is going to be GCD of 6, comma, 18 mod 6. What's 18 mod 6? It's 0, right? Because 6 actually is a divisor of 18. There's no remainder. So 6, 0. Finally, we can use that first rule and tell this is equal to 6. That's what we expected. We definitely shouldn't use the second rule if B is 0, because A mod 0 doesn't make any sense. It's not really defined, so we can't divide by 0. Okay, let's do another example. I think, way back when we first started talking about GCD, I put an example on the board of 2 numbers, and I said, can you find the GCD of these numbers? And they were kind of biggish, so right, and we said, well, we could factor them, but that didn't sound like fun. So let's see how this works. I think those are the numbers that I have. At least those are the numbers in my notes here. I'm pretty sure they're the same ones. All right, well, let's use the second rule. GCD of, the second number is 7811. And then here I have to put 7169 mod 7811. What is that? It's kind of a trick question. So it's actually 7169, why?
It's first, so if you divide it, you get 0, and then
That's right. I'm taking 7169 divided by 7811. I mean, 7811 is bigger than this, so it won't fit in even once. So the quotient is 0, and the remainder is just 7169. So it seems like we haven't really made any progress, but we have. Right, notice they actually kind of switched places. But they're not going to switch places back, because now we're going to do 7811 mod 7169. We're going to get something small. So yeah, sometimes when people write down a definition of how to do the Euclidean algorithm, define the GCD, they'll first say, well, like, okay, first, if A is less than B, then switch them, and then go on and do. You don't actually need to say that, because this rule automatically switches them. If you start out with something with A being less than B, you'll just get B here, and then A mod B will be,
So you're kind of just saying like, whatever the two numbers, like whether one is bigger or whatever, you just do like if you just do the second step enough times, and then whenever you get to the point, you'll be able to do that first step, like with any condition.
Yep, that's right. So, yeah, I'm just saying, and here I was saying, if you happen to start where the first number is smaller than the second number, the very first time you apply the rule, they'll switch, and then from then on, the first number is always going to be bigger than the second number. Because you're always going to end up with B and then something mod B, which is going to be smaller than that. All right, let's keep going. So let's see, so this, we get 7169 here, and then 7811 mod 7169. So I don't know about you, it looks to me like that's going to fit exactly once, right? And then we'll have whatever, 7811 minus 7169 left over. Anyone know what that is?
642.
642, thank you. Okay, and then we'll do GCD of 642, 7169 mod 642. And again, like, you know, if you're doing something like this on a module, I don't expect you to do this in your head, or like, just put it in the calculator, or use Disco, or whatever. But it turns out that 7169 mod 642 is 107. You can take my word for it, or you can check later in the calculator. So this is equal to GCE of 107, and actually 107, 642 is exactly 6 times 107. Yeah, so 6 times 7 is 42, 6 times 100. So the remainder is going to be 0. So now we see that the GCE is actually 107. And now that we know that the GCE is 107, actually we could factor them very easily now, because I know that 107 is a divisor of both. So if I just like divide both of them by 107, I can see what's left over, which will be a much smaller number. I think, in fact, in this example, I chose them both so that it's like, it's some other prime times 107. So like 7169, I think, is 107 times 67. And 7811 is 107 times 73. So yeah, if someone gives you a really big number and says this number is, you know, is the product of two very large primes, you know, find them or else, you know, I'm going to kill you, then in that case you should like start thinking about ways to escape, because you're not going to be able to do it. But if you happen to have two numbers which are products of big primes, and you know that they have a shared prime, then you can just use the Euclidean algorithm, find their GCD, and then divide by that, and you can very easily factor them both. This was actually, there's a funny, not exactly a story, but just like some researchers kind of realized that the way that some Wi-Fi routers were generating encryption keys, which involves picking very big primes and multiplying them to generate a key that's hard to undo because you can't factor them. But it was like not using sufficient randomness, essentially. So like, there was a much higher chance than there should have been that two different routers would happen to choose the same prime, like one of the primes the same. It should be like impossible that ever happened, but it happened sometimes. And they were able to like get a whole bunch of encryption keys from lots of different routers and just like run GCD on all of them, and like were able to break a whole bunch of them because they happened to share primes. So that is an interesting way this affects security. Cool. Any other questions about this is in fact extremely efficient. And if you many of you may end up taking algorithms with me. One of the assignments that we do in there is I actually walk you through analyzing kind of how efficient this actually is. But essentially, the number of steps that you need is proportional to the number of digits in these numbers. So, and that's really good, right? So if you have like 100-digit numbers, those are really big numbers, right? Factoring them is going to be impossible. But you run this algorithm, it takes about 100 steps. Or maybe like 200 steps or 500 steps, but not like a million, right? Maybe like a few hundred. Which, for a computer to run this algorithm for 100 steps, I mean, it's like, it would take you much longer to blink, right? And so GCD is used all the time, and it's very, very efficient. Okay, so we've got a few minutes left, so I want to go back to our frog. Think about this a little bit. So, our conjecture here was that, well, in this case, right, the GCD of 30 and 18 is 6, and we actually showed that in this case you can reach any multiple of 6 by adding or subtracting copies of 30 and 18. And the question is that always going to be possible? If I have A and B, can I add and subtract copies of A and B to always get me the GCD? I definitely am not going to be able to get anything that's like smaller than the GCD, because like anytime I add and subtract copies of A and B, it's gonna be a multiple of that GCD, right? So I can't get anything smaller than that. But maybe it's not even possible to get that at all, but it is. So this is a theorem. This is called Bézout's theorem, named after someone named Bézout. I don't know anything about them actually, but so probably the fact that this theorem is named after this person means that someone else came up with the theorem, because that's just how things get named in math. I don't know why. But here is the theorem. So we have A and B, natural numbers. Right, what we want to say is, I can add or subtract some number of copies of A and B to get their GCD. Okay. So then there exist, we'll call them S and T, which are integers, such that S times A plus T times B is equal to the GCD of A. Okay, so like, if A represents how big our jumps are and B is how big our hops are, then S is telling us, how many jumps to do, and T is telling us how many hops to do. And S and T can be negative, right? So it could mean, jump this way and then hop back. But how many do we have to do to reach the GCD? And once we can reach the GCD, then by our argument before, we could actually reach any multiple of the GCD by just repeating that process if we wish. And so this theorem says, yes, actually you can always do this. There's always some way to add up copies of A and B to get their GCD. We don't have enough. I will prove this next time. We don't have enough time to finish the proof. So yeah, what we'll do next time, we will actually prove this, and we'll actually show how to. So the proof, interestingly, doesn't really tell us how to find S and T. It just kind of shows they must exist. Kind of unsatisfactory, but then we're going to talk about there is a way that you can actually find S and T. It's basically the Euclidean algorithm with some extra stuff. So you like keep track of some extra stuff while you do the Euclidean algorithm. So like while you're computing the GCD, you can also be keeping track of some stuff that tells you what S and T should be. And that's really important, and that has a bunch of applications. It's going to let us solve more kinds of modular equivalences. It's the basis for